In this lesson, we're going to introduce the quotient rule for derivatives. This will be the last derivative rule we need to find derivatives of arithmetic combinations of functions. We'll begin by introducing the quotient rule and looking at some ways to remember it, and then we'll look at a few examples of how to apply it. Let's introduce the quotient rule. We'll state the rule first. Of course, the quotient rule is to take derivatives of quotient functions. So you can think of a quotient function as one that can be expressed in the form u over v, where u and v are functions. And just like the product rule, the quotient rule is a little more complicated, especially if you compare it to something like the sum rule or the difference rule. In fact, as we'll see in a second, the quotient rule looks the most complicated probably of all of our derivative formulas. It's not necessarily the most complicated to apply. It's a formula and you plug stuff into it, but it does certainly look complicated, and remembering it can be a little challenging. I'll mention a little technique you can use to remember it after we've introduced it. Here's a statement of the quotient rule. It says that the derivative with respect to x of u over v is v times u prime minus u times v prime over v squared. So there are two parts to this. There's the numerator and the denominator in the derivative. Notice that the numerator looks a lot like what we get from the product rule, except instead of using addition, we use subtraction. The product rule would have a plus sign there. And this is important because the order then matters. With the product rule, you're adding, so the order of the terms isn't very important. But in the quotient rule with subtraction, you really need to remember the order of the terms in the numerator. In the first term, we have the derivative of the numerator function, u, times the denominator function. So v times u prime. And then those switch in the second term. And then in the denominator of our derivative, we have v squared. So we take whatever function appears in the denominator of our starting quotient and we square it. The important thing to remember here is that it's v that appears there, not v prime. We're squaring the denominator as given to us, not its derivative. That is the quotient rule for derivatives. It can be a little difficult to remember. Here's a little trick. This is kind of a little bit of a whimsical device you can use to remember the quotient rule. The way we'll do this is to take the quotient u over v and assign slightly different names to its parts. We'll have the high part, the numerator, and the low part, the denominator. And then the derivatives of those we can denote as d high and d low. D high for the derivative of the numerator, d low for the derivative of the denominator. Now, here is what the quotient rule says is the derivative of u over v. But if we put this in terms of high and low, it comes out like this. Low d high minus high d low over low low, or low times low. So you can kind of read that and almost make a song out of it. Low d high minus high d low over low low. It sounds like something that you might hear in like Snow White and the Seven Dwarfs or something like that. It's a little corny, but that is a useful way to remember the details of the quotient rule and how all the parts fit together to give you the entire derivative. Let's look now at some examples of the quotient rule in application. Our first example will be about as straightforward as an application of the quotient rule gets. It'll be a typical rational function. We're going to find dy dx, given that y is equal to 5x minus 2 over x squared plus 1. So notice we're dealing with a quotient function here, 5x minus 2 over x squared plus 1. So we can find the derivative by using the quotient rule. Here are all the parts. Now there's a lot here. Let's break it down piece by piece. In the numerator, the first thing we have is x squared plus 1, the denominator of our quotient function, the low part, if you will. And that's being multiplied by the derivative of the numerator, 5x minus 2. So that's our low d high. We then subtract the numerator, 5x minus 2, times the derivative of the denominator. So that part after that middle minus sign is high d low. And then in the denominator, we take x squared plus 1, which is the denominator of our original quotient function, and we square it. The next step is to find the two derivatives in the numerator. These are both fairly straightforward. The first function there, 5x minus 2, is a linear function, so its derivative is its slope, 5. And the second function, x squared plus 1, is a polynomial function, and we can find the derivative of that by using the product rule, the power rule, the sum rule, and the constant rule for 1. And it ends up being 2x. If we then distribute the 5 and the 2x, this is what we get. And then we can finish by combining like terms, and we end up with this, negative 5x squared plus 4x plus 5 over x squared plus 1 squared. That is the derivative of the quotient function with which we started. In our second example, we're going to do a slight algebraic manipulation of our starting expression in order to make the work of applying the quotient rule quite a bit easier. So our goal here is to find the derivative of this quotient function, 3 minus 1 over x plus 5. If we just start applying the quotient rule at this point, things are going to get a little complicated because of the 1 over x that appears in the numerator. We have a complex fraction here, and applying the quotient rule would require us to continue working with complex fractions, which can be a little bit unwieldy. So to make things a little bit easier on ourselves, let's multiply the numerator and the denominator of our function by x. As long as we multiply both the numerator and the denominator by the same thing, we can do this kind of thing all day because all of our expressions will be equivalent. So this is our goal, to find this derivative. But because these two expressions are algebraically equivalent, we can find the derivative of the second item you see here, where we multiply the numerator and the denominator by x. And if we distribute the x into each binomial there, you can see that the fraction in the numerator goes away. We now just have 3x minus 1 over x squared plus 5x. And now we just have a polynomial over another polynomial. And this is about as straightforward at this point as an application of the quotient rule gets. So to take this derivative, we'll go step by step here. We take the denominator, the low part, and multiply it by the derivative of the numerator. 3x minus 1 is linear, its slope, and so its derivative is 3. That's the first part of the numerator. We then subtract the numerator function, 3x minus 1, times the derivative of the denominator. The derivative of x squared plus 5x is 2x plus 5. And then we divide all of that by the square of our function's denominator. So that'll be x squared plus 5x squared. And again, at this point, all the work is algebra. We'll distribute the 3 and multiply 3x minus 1 by 2x plus 5 using FOIL. And then we'll combine like terms, and this is the result we obtain. Negative 3x squared plus 2x plus 5 over x squared plus 5x squared. That is the derivative of the function we started with. Our third example will involve a function where the denominator of the quotient is constant. We're going to find y prime, given that y is equal to x squared plus 3x over 6. Now, you might look at that and say, oh, we've got a fraction here. We've got a quotient. We need to use the quotient rule. And you can do that. You will obtain the correct derivative function if you start applying the quotient rule. But it's complicated because the quotient rule is kind of complicated. There's a much easier way to do this. Instead of thinking of this as a quotient of two functions, one of which is constant, let's think of it as a polynomial with a constant multiple. So think of y here as 1/6 times x squared plus 3x. That's equivalent, but we can find this derivative simply by taking the derivative of x squared plus 3x and then multiplying the result by 1/6. That's using the constant multiple rule. The derivative of x squared plus 3x is 2x plus 3. That's getting multiplied by 1/6. And if we distribute 1/6, we get 1/3 x plus 1/2. That's the derivative of the function we started with. And finding it that way is much easier than using the quotient rule and its fairly complicated formula.